Okay, welcome. Here's a recap of week one. So week one was the classes on February 2nd and February 5th. Here's our schedule. Remember, we met for a full class at the beginning of Tuesday, and then the three groups split up into doing three different activities. Our first topic was relations, and it was a collection of ordered pairs. So I wanted to point out with this, G is the name of the set, and there's a set bracket, and then it's ordered pairs. Here's an ordered pair. There's a first coordinate, and there's a second coordinate. And this associates the first coordinate, moon. Let's put moon over here, with the letter M. Why? I don't really know. But then the second ordered pair associates the word frog with the letter R. And then the third coordinate associates moon with the letter O. So let's put the letter O over here. It's the same word, moon. And then the last order pair, frog, comma, O, associates frog with the letter O. And this set of the first coordinates, it's a set, it's called the domain of G. G is the relation. And the second coordinates, M, R, O, that's called the range of G. Okay, so let's move on. A relation doesn't have to be anything, and normally we just put numbers, ordered pairs of numbers. So if we put, take a look at this one, F, the domain, -2 is in the domain, and that connects to -1, which is in the range. So I'll label that range. And then the next ordered pair, -1, is also in the domain, so we'll make 2 copies. And that corresponds to 1. -1 goes to 1. 0 goes to 3. 1 goes to 5. And finally 2 goes to 7. And this is called the domain. I'll put a set around it, that's Euler notation, and a set around the range. And one thing that I notice here is that every element of the domain corresponds to one and only one element of the range. So there's only one arrow coming out of each element of a domain, and if that's true, we call it a function. And that's what it is. A function is a relation, but each possible input, every one of the inputs leads to exactly one opposite output value. And so this was the domain from the last function, f. Here's the range. And it wasn't just a random set of ordered pairs. There's actually a rule to it. The rule was that you would multiply by 2 and add 3. Let's try it. 0 is the easiest one. Take 0. If we put it into this function, boop, multiply by 2. 2 times 0 is 0. Add 3. We get 3. And out comes 3. And so that's why 0 corresponds to 3. There's actually a rule for that that goes through the function machine. Okay, so each of these functions, every function can be represented in different ways. There was strictly speaking, it's a set of ordered pairs, but we can often describe what the rule is in words. Multiply the input, blah, by 2 and then add 3. We can make a table to describe what's happening. There's an expression like 2x plus 3 means multiply x, which is the input, by 2 and add 3. And then one other representation is the graph. In the graph, the horizontal axis is the x-axis, the vertical axis is the y-axis, and so a point like this has coordinates. Well, there's 1. We think of 1 as the input, and then this number is 5. 5 is the output, and we can record that here as well. The inputs are x's and the outputs are y's, but we can also graph each of those points on the plane. It's called the Cartesian plane, and so it looks like things are in a straight line. However, the domain is just those 5 numbers, not all real numbers. Let's continue. So here's a relation. Question, is this a relation of function? This relation is a set of integers, and we can write this in set builder notation. It's the set of ordered pairs x, y, and then the condition is that x and y are integers. Okay, they have to be whole numbers integers, and they have to make this equation true. The square of x plus the square of y is 25. And that's a description of the relation in set builder notation. Over here, the graph is actually more illuminating. It's a point like this. Here's x is 0, y is 5, and 0 squared plus 5 squared, that is 25. So 0 is in the domain, and 0 will point to 5. So we could actually just go through, and let's go in the counterclockwise direction. What is this? This is counterclockwise is the mathematical direction. So here's -3, that's the input, and the output is 4. So I'll put -3 here, and the output is 4. And this one, that's -4 is the input, the output is 3. And this one, the input is -5, and the output is 0. So far, no repeats. So far, each input is corresponding to just one output. But let's see, this one, -4 goes in and -3 comes out. So -4 has 2 arrows coming out of it. So it's already, I know it's not a function because one of the possible inputs does not have a unique output. Let's finish this up. This one is, it's like -3 is going to -4. This one, 0 is going to also to -5. And here, 3 is going to -4. And 4 is going to 3. 4 is going to -3. Now it's getting complicated. And 5, let's squeeze that in here. 5 is going to 0. And this one, 4 is going to 3. It's all the way up here. And this last point, there's 12 points in this function. 3 is going to 4. So there's the domain right there. And here's the range right there. It's not a function because there's actually many numbers in the domain. Many elements of the domain correspond to multiple elements of the range. So we've been talking about sets and never quite defined it, but a set is a fundamental object in mathematics. Here's a well-defined collection of distinct elements or members, and that's usually numbers. But not always. We saw that relations and functions are sets of ordered pairs of numbers, not just numbers themselves. And an Euler diagram for a set is where you take the elements of a set, maybe write them down, and then put a blob around it, like I have here. Roster notation, this is where you have just a list, and you separate them with commas. The order doesn't matter, but we need a set bracket and a set bracket, and then we have them separated by commas. And set builder notation, that's more sophisticated. And in the first part, well, there's a set bracket, but then we say what's in there. So this says that there are integers that we're calling n. Integers are in the set z. Z is actually from the German word for number, Zahlen. I guess the German mathematicians named the set of integers. And then over here, this is a condition that has to be met for the number to be in the set, and has to be between 1 and 4, and it's allowed to be 1, and it's allowed to be 4. And so the only 4 numbers that satisfy that condition are 1, 2, 3, and 4. A little bit later we'll see interval notation, because we're going to be looking for sets of numbers on the real number line. There'll be infinitely many numbers in an interval. We can't use roster notation because we can't list an infinite set, and we want to find a better alternative than set builder notation. If you're bored, here's something to think about: Russell's paradox. When a set has things in it, maybe it's possible for a set to include a set, and maybe a set can include itself, which is kind of weird. So let's say that's more normal for a set to not include itself as a number. Well, then we're going to say S. S is the set of all of these normal sets, the set consisting of all those sets that don't include themselves. And Bertrand Russell, the famous philosopher, asked the question, does S include itself? And think about that. That's really an aside from this course. And let's go on to interval notation.